Today, we've got a fascinating story for you. It's a tale of two absolute giants in the world of natural gas. First, there's Groningen in the Netherlands. Let's call it the Old King, which is being shut down for good, even though there's a staggering amount of gas left in the ground. And then you've got Sakarya, the young challenger, just starting up in one of the toughest environments you can imagine, the deep, dark waters of the Black Sea. So, what's the deal? Why would you walk away from a fortune in energy only to spend billions chasing another? That's the puzzle we're going to piece together. Okay, let's just dive right in. This here lays out the whole paradox perfectly. On one side, you've got Groningen, shut in, a giant put to sleep. And its big problem, man-made earthquakes. On the other side, Sakarya, just getting started. And its main challenge, sand production. That means the rock itself is literally falling apart and threatening to destroy all the equipment. See, these aren't just little technical glitches. These are the fatal flaws that sealed the fates of these two fields in completely different ways. Now, to really understand what's at stake, just look at this number. 450 billion cubic meters. I mean, that is a crazy amount of gas. To give you some perspective, that's enough energy to power the entire United Kingdom for more than 6 years. So this isn't a field that's run dry. No way. It's been abandoned because the price of getting that gas out is no longer about money, it's about the safety of the thousands of people living right on top of it. All right, so to really solve this mystery, we've got to put on our geologist hats for a few minutes. We need to rewind the clock. I'm talking hundreds of millions of years to see how these two giants were even born, because their geological DNA, well, that's the key to everything. So let's start with our old king, Groningen. I want you to picture this. It's about 250 million years ago in the Permian era. The supercontinent Pangaea is the only landmass around. And the spot that will one day be the Netherlands, it's a huge, dry desert with massive dunes shaped by powerful winds. And this is exactly why, for decades, Groningen was considered a geologist's dream come true. You see, those ancient wind-blown dunes created this incredible reservoir rock. The sand grains are all about the same size, which means lots of space between them for gas. The rock itself is solid, stiff, it's like a giant, continuous sandstone sponge. And the cherry on top? A perfect, self-healing layer of salt that trapped all that gas for millions of years. It was simple, predictable, and absolutely massive. Okay, now let's jump in our time machine and fast forward to our young challenger, Sakarya. We're talking about a much, much more recent time, geologically speaking, and the setting could not be more different. We're not in a dry desert, we're at the bottom of the Black Sea. And this reservoir wasn't built by wind, but by these massive, chaotic underwater avalanches of mud and sand. And right here, you see the total opposite of Groningen's beautiful, neat structure. Instead of one giant sponge, Sakarya is this messy, jumbled collection of channels. The sediment is unconsolidated, which is a fancy way of saying it was never buried deep enough or long enough to turn into strong, solid rock. It's basically just weak, loose sand mixed with mud, a real complex maze. This table just puts it all right there, side by side, and the differences are, well, they're night and day. You have an ancient, stable basin versus a young, dynamic one. But the most important line is right there at the bottom. Consolidated, strong sandstone versus unconsolidated, weak sandstone. Their fundamental building blocks are from completely different worlds. So what does all this geology stuff actually mean? Well, it means these different origins create two totally different problems. These fatal flaws that don't show up until you start pumping out the gas. One field is literally shaking the ground, while the other is in danger of just crumbling from the inside out. With Groningen, the problem is huge. It affects the entire field. Think about it like this. For millions of years, the gas pressure helped hold up the rock. You take the gas out, and that support is gone. So the immense weight of the earth above starts squishing the sandstone. That squishing puts a ton of stress on old faults deep in the earth, and eventually one of them slips. Boom, you get an earthquake, right under people's homes in a place that never had them before. Now, a 3.6 magnitude earthquake might not sound like a huge deal if you live somewhere like California. But in this region, where buildings were never designed to shake, it was a catastrophe. The 2012 Huizinga earthquake caused widespread damage and, more importantly, widespread fear. That one event was really the final straw. It proved the risk was just too high, and it sealed Groningen's fate for good. Sakarya's problem is the complete opposite. It's microscopic. That rock we talked about, that weak, loose sand, it's not strong enough to stay put.
When you pull the gas out at high speeds, it just rips the sand grains right along with it. And that turns your gas stream into a high-velocity sandblaster that literally tears apart your multi-billion-dollar pipes and valves from the inside. It's a self-destructing reservoir.
Okay, so you've got two giants, each with its own personal kryptonite. How on earth do you deal with that? Well, as you're about to see, the engineering approaches are polar opposites, pushing right to the very edge of what's possible. For Groningen, the engineering wasn't a battle. It was a carefully managed retreat. It was all about slowing down the inevitable. They put strict limits on production to try and slow down the shaking. They built these huge compressors to suck out the very last bits of gas. But at the end of the day, you can't stop the Earth from compacting. The only real solution was to just walk away.
Sakarya, on the other hand, is a full-on technological assault. It's a proactive, high-tech attack on the geology from day one. We're talking complex filters down in the well to stop the sand, robots, chemical injections to keep the pipelines from freezing up, and smart wells that can choke back problem areas. I mean, think about what they're doing. It's basically remote-controlled keyhole surgery on a rock formation 2 kilometers under the sea to stop it from destroying itself. It's incredible.
And they have to do all of this in water more than 2,000 meters deep. That's over a mile straight down, in the pitch black. This is the absolute frontier of engineering, where you can't send people. It all has to be done with robots and remote systems. Absolutely mind-boggling. So, we've gone from ancient deserts to the deep sea floor. After all that, what's the big takeaway? What are the legacies these two giants are leaving behind for us? Groningen's legacy, well, it's a powerful cautionary tale. It's a stark reminder that even the most perfect-looking geology has a breaking point. It teaches us that when you disturb the deep earth, the consequences can be permanent and severe, so severe that you have no choice but to walk away. Sakarya's story is still being written, but for now, it's a testament to unbelievable technological ambition. It shows us the game has changed. Success on these new energy frontiers isn't just about finding the gas anymore. It's about having the incredible engineering precision to manage, not conquer, but manage a hostile environment every single day. You know, it really all boils down to what the experts who study these fields said. For Groningen, the key phrase is, stress memory is permanent. The damage done is irreversible. For Sakarya, it's geology is heterogeneous, meaning the challenge is constant, unpredictable complexity that you have to deal with every second of every day. And that leaves us with this final, really important question for our energy future. Groningen shows that the easy resources we've relied on for so long had a hidden, terrible cost. Sakarya shows the insane complexity and expense of what comes next. So the question we have to ask is, as we search for energy in harder and harder places, are we just trading old, unforeseen problems for new, incredibly complex ones? That's a geological puzzle we're all going to have to face.